So this is the second set of slides with respect to simple harmonic motion. Unit 6 in AP Physics C only has one subsection. So this is the second set of slides, and in this set we'll be talking about energy. Okay. Just to repeat, these are the same slides that we saw in the previous one, so I'm going to go through these without comment until we get to the energy ones. Here we have some important formulas. The very important formula here of d squared x dt squared is equal to minus omega squared x. Some more essential knowledge. And here we have the energy. So this is where we start the energy aspects. Okay, and potential energy for a mass spring is going to be equal to 1/2 kx squared. For a simple pendulum, it's going to be mgh, and we'll review that. For any other system, it may get a little more complicated, but they're outside of the range of what we're doing here. But always be ready to try and make some extrapolations and apply what knowledge you know. Okay, so that's the spring energy. And here we have the total energy aspects and the kinetic energy. You should be familiar with all of these anyway, and total energy is going to equal the sum of the two. Okay. And we'll go over what it means to be 1/2 k a squared or equal to 1/2 k x squared max. Okay. The period equations we've already talked about, so I'm not going to review those. Okay. Again, we've also seen the IB formulas. Some of these, the two on the bottom left, energy kinetic 1/2 mv squared, except now we're going to be looking at it from an omega squared position aspect, and same with the total energy. Okay, so another way to think of SHM is in terms of energy, okay, because simple harmonic motion is the constant interchange of energy from one form to another. If I have a pendulum, the potential energy becomes kinetic in the middle, and then it becomes potential as it swings past to the other side, etc., etc., etc. And this is true for all simple harmonic motion systems, okay? Some form of energy, oftentimes potential, becomes kinetic, becomes potential, becomes kinetic, etc. Okay, so when do I have energy minimas and maximas? Because those are going to be very important points and allows us to calculate, because when one energy is at a minimum, the other energy form is at a maximum, and the minimum is usually going to be 0. Okay, so at the amplitude points, it's always useful to have a concept of mass spring or a pendulum or even both, okay, running in your head when you're going over these, okay? So at the amplitude points, the potential energy is a maximum. If I'm thinking about a pendulum, that's the maximum height, or if I'm thinking about a mass spring, it's the furthest edges, okay? So at that point, potential energy is going to be 1/2 kx squared, or in a pendulum, it's going to be mg delta h, okay? And at the equilibrium point, kinetic energy will be a maximum and potential energy becomes 0. Okay, so at the pendulum, that's the lowest point. That'll be our 0. In the mass spring, delta x is 0, and so therefore 1/2 k delta x squared is also 0. So it's important to have these two kind of views and think, okay, where's my potential energy going to be a maximum? Where's my kinetic energy going to be a maximum? Okay, and just to refresh you that h in the pendulum is going to be L minus L cosine theta. We'll see that in a little bit in the coming slides. Okay, so just to summarize, this table is very useful to either derive or memorize. Derivation is really simple, so I recommend that you derive it rather than waste the brain energy trying to memorize this. Okay, so understand where your position is going to be a minimum and when it's going to be a maximum. So at the equilibrium point, your position is in the middle, obviously the minimum. At the amplitude points, you're the maximum displacement from equilibrium. Okay, velocity is going to be the opposite of that. Acceleration is the same as position because F equals ma. And so the greater I am displaced, the greater my force will be. Ma equals kx. Okay, kinetic energy, because it's 1/2 mv squared, matches your velocity function. Potential energy would be the opposite of that. Okay, so be able to derive this. It should take you less than 30 seconds to derive this table. Okay, so in general, okay, so besides at the equilibrium or the amplitude points, sometimes we'll need to calculate this. Okay, so at the amplitude point, okay, x sub 0, okay, because that's usually where we release it from, okay, the kinetic energy is going to be 0. I released it, so it started from rest. Okay, velocity 0, kinetic energy 0. But that's also where I have the most potential energy. And because total energy is the sum of those, my potential energy would be 1/2 k x sub 0 squared, x sub 0 being my amplitude. And therefore, total energy is going to be the same thing because all I do is add those two together. And since Ke is 0, fine. Its total energy is nothing more than 1/2 k x 0 squared. At any other point x, okay, between 0 and x sub 0, my potential energy is going to be simply 1/2 k x squared, and kinetic energy is total energy minus potential energy. Okay, going through a little bit of algebra, it basically says that 1/2 mv squared is equal to 1/2 k x sub 0 squared minus 1/2 k x squared. Okay, solving that for v, we find that v is equal to omega times the square root of x sub 0 squared minus x squared. And this is where we see the IB version of the formulas. Be comfortable with this derivation as well, because these formulas are not on the AP formula sheet. Okay, but if you remember how to approach this, you can easily solve this formula. Okay, perhaps not with the omega, but you can see that omega is equal to simply k divided by m. So that derivation was from the previous set of slides. Okay. Continuing this generalization, if that's my velocity, my kinetic energy, here's the formulas we see from IB. Kinetic energy, E sub k, is equal to 1/2 m omega squared times the amplitude squared minus position squared. Total energy is simply 1/2 m omega squared amplitude squared, and potential energy gets rid of the x sub 0, and you just have an x. So we can see now how useful omega is, and the derivation that we did in the previous set of slides is going to be very important. Okay, so I recommend going back and redoing those practice questions, as well as reviewing the slides with the derivations for a spring and a pendulum. Okay, so just to move on, because a lot of times we'll see graphical versions of SHM, and we need to be able to pull information out from these graphs. I'm going to review these graphs here. Okay, first we have time graphs: position time, velocity time, acceleration time. And the tricky one could be energy time. Okay, we'll also see position graphs where the x-axis is position. We'll see either force or acceleration positions and energy versus position. And again, the more comfortable you are with these and being able to pull data from these, the better off you're going to be. Okay, so here we have our three position, velocity, and acceleration graphs. Okay, if you remember how we got there, displacement is a cosine omega t. Can I get omega from these graphs? Okay, if I have displacement and velocity and a y-axis, okay, the velocity is just going to be omega times a, whatever those numbers are, if they're giving me numbers. And acceleration would be omega squared a. So those are the limits of my sine and cosine functions. Okay, but I can get omega just from the x-axis as well. If I have numbers for the x-axis, okay, then the numbers will give me period, because period is on the x-axis. Okay, and so 1 period is a full up and down. So for the displacement, or actually for all the graphs, the period will be the same. It's 2 seconds in this case. Okay, so if I have period, remember omega is going to equal to 2 pi divided by period t. So in this case, my omega would simply be pi. And if you have omega, you can get to k over m or L over g for the spring or pendulum situation. Okay, so this is a combination of the three energies: total energy, kinetic energy, and potential energy. Okay, so here I have potential energy in, actually you can't tell, actually they're labeled. So potential energy is in blue, kinetic energy is in red. Notice how they are 180 degrees flipped from each other. Okay, and total energy is just a flat line. So be careful because sometimes they'll try and trick you with total energy when you think they're talking about potential or kinetic. Okay, so again, I can get the period and omega from the time axis. You do have to be careful because remember, your velocity is squared, 1/2 mv squared. And v was a cosine or a sine function. Since it's squared, it's all positive. So to find period in this case, I have to remember that I need to go 2 full hills over. Okay, so following the blue one, okay, I first have to go up and down, okay, 1 hill, or actually I start down 1 hill, up another, and then down a hill, up another before I get an entire period t. Okay, so you do need to be a little bit careful, actually very careful. I personally have missed this question many times. Okay, so just remember that if they're talking energy, you need to go 2 hills over because of the 1/2 kx squared or 1/2 mv squared aspect. Okay. Next, we have force or acceleration versus position. Okay, so always double check your axes, double check your units on the axes. That's going to be important. So this is the graph of force versus position for a spring. You can see the minus kx aspect. So amplitude is going to be the greatest position. In this case, it's shown as 5 or -5. Sometimes it'll be given in text and your graph may extend beyond that. Okay, so just be a little bit careful. And guess what the slope is? Okay, your slope is that spring constant k. You do have to remember throw out the minus sign because it's minus kx. Okay, so if I'm going to get omega from this graph, I'm actually going to need mass. I cannot do it simply from this graph because k divided by m is going to get me my omega. So omega is equal to the square root of k divided by m. Okay. Just to continue that, if you wanted to get potential energy, you can, because potential energy is the area under the curve, because that's just work. Okay, force times displacement, or integral of force with respect to distance. Okay, a little bit easier would be if I had an acceleration graph. In this case, my y-axis is acceleration in meters per second squared, and my position again is in x. It's effectively the same graph, just different units on the y-axis. And my slope now is equal to k divided by m, or omega squared. Okay, so x max is going to be my amplitude. It's shown here, 5 centimeters. And I can easily calculate period and such from that slope. Okay. Last one, okay, position graph for energy. So here I have my energy. Again, you can see from plus A to minus A, those are my amplitude points. Position, my kinetic energy is again in red. Potential energy is again in blue. Total energy is the flat line on top. Okay, I can get the amplitude points from the graph when my kinetic energy hits 0, just in case they extended it past there. You can never have kinetic energy negative, so always stop there. Either way, I'm still going to need mass to get omega because I can only get 1/2 mv squared or 1/2 k x squared maximums from this graph. Okay, it's also important to notice where they're equal. When does my potential energy U equal my kinetic energy K? Okay, obviously where they intersect, but positionally speaking, it's not at the halfway point. Okay, if I go straight down from here, it's somewhere in this aspect, not in the middle, which would be 1, 2, 3, which would be the third line. I'm actually a little bit past there. It's almost like the 2/3 point. I believe it's actually the 3/4 point. Okay, so I need mass to get omega otherwise. Okay, so we'll see some of this in our practice. Thank you.